hopefully a little bit shorter than usual stream, because I just realized as I was typing in a new blog post about my air conditioning reverse engineering series that I don't have some screenshots that I want, showing how the I²C serial ports over UART work, like how the I²C connected physical discrete UART behaves. So trying to get that done, I decided, well, let me just stream it, because it's going to be a little bit of setting up the analyzer. And while I'm at it, I may do a little bit more CircuitPython stuff on the SC16 IS741A library, because right after I implemented it pretty much on the Adafruit's Discord, then H pointed me at, but pointed someone else actually, at the CircuitPython library for register access, which is extremely nice, and I would like to use. But yeah, right now it doesn't, like, right now I'm not using it, so I should start using it. So let me start first with, there is a little bit of refocusing, as it turned out, because I forgot to set this in focus first. There we are, I want to say. It's going to be as in focus as it's going to be about this. Let me set up the breadboard. So this is the same breadboard as the last time I did CircuitPython stream. The trinket M0 over here. Now it's actually much easier to see when I do stuff. But the trinket M0 is over here on the side. These are the SCL and STA. I never remember which one is which, but I'm just going to go and connect them with the same color on this thing. This one is the VRX? No, what's the reset? Oh, that's the clock. Sorry, I was like, which one is which? The orange one over here is the clock. The blue one is the reset line. The idea is that once this resets, when it starts up, it also resets the SC16. And the brown line provides the clock, which I originally used this crystal over here, which is a 1.8432 megahertz clock, which turns out to not actually be necessary, because I can provide a much slower clock straight from the trinket, so that works for me. I'm going to start by wiring this, and while I'm at it, like I actually posted today on the blog, or I left it published today on the blog, because I write the posts well in advance and I usually just queue them up, although I don't have anything for next week, so I need to actually write it, thus this stream. I've been making harnesses for my Sally analyzer, like this one, and the way I'm doing it is I'm just grabbing actual DuPont jumper cables. These ones are coming straight from AliExpress, as you can imagine. Wait, and either male, female, or female, male, depending on what I need to use. And I just use a 2x4 out, 2x4 housing, 2x4 case, 2x4, whatever you call the thing, to connect all of them together on this side. So I essentially just have 5 wires going into that thing and then coming out that way, but it allows me to just connect the cables as I need them. So I'm going to connect this to the ground, which is this one. Going to connect the yellow as yellow and the green as green. And then I'll figure out which one is the clock and which one is the signal. And so I should look up the data sheet I want to be sure, but I remember putting this orange here, so that should be the transmit of this serial, which is all I need. That's literally all I need. Let's go to analyzing. Is logic 2 actually connected? Not yet. No, it is. And then let me connect this thing. Okay. Connecting the Logic Pro. And I'm going to grab this yellow cable over here. Let me actually get it. Ah, no pull-up found for STL or SCL. No, it is. It just it's out. Is it working? No pull-up found. What the heck? Oh, it's missing one pull-up. Actually, it's right. Let me. Are these the same pull-ups? Yes. Both of these need to be pulled up. Let me just cut these two to size. Tell me if this one works better. Like the microphone gain here is nearly to the maximum. Okay, so I'll try to keep this nearly to the maximum on the input gain. I have a feeling that possibly the YouTube processing is making it better by simply normalizing the volume on their side. And YouTube is the main way I actually notice this usually. So this needs to be pulled up. One pull up. Doing the same on this one. Yeah, same. I mean, the last thing YouTube will want is for people to complain that every time they change between one video to the next, the volume widely changes. Although I think LGR is a little louder to me than, say, Tecmon, but I think it may just be their voice. Second pull up here. Yeah, okay, now it seems to be fine. It's not erroring out. So if I start this, I'm going to actually clear all of this. I'm going to record the first three. Yeah, those are not meant to be. Okay, stop. This is all set up for the previous thing. Like, since this is going to this is the setup for when I was doing this other breadboard over here, which was the actual link bus, the 2 USB serial, and the 12 volts bus. That's not what I'm doing today. Actually, I can disconnect this because I'm not going to need this anytime soon. So I'm throwing this to, not throwing, but leaving this to the side. This needs to go into one of the project boxes. I need to also clear the analyzers. I wonder why there is no clear all the analyzers. So if anybody from Sale is looking at this video or happens to be looking at the live or anything at all, please, would be nice to have remove all of the analyzers because I'm starting clean. Okay, so that's better, I guess. Yeah, so that's clearly the clock, or it looks like the clock, and that's the data. So I²C SDA is 001, and SCL is 00. And now these are not going to be and I'm going to try to remember, but oh, this is a single color, right? Yeah, it's a single color. That's okay. So that part is fine. The orange is not TX, but maybe RX. So let me see. Where do I have browsing? There you go. And doesn't find Edge. Edge. There you go. No data classes right now. No async. All the async stuff is fine. This is a till-in one, but still not the one I want. Data sheets. The SC. I have like 3 components that start with S. There are 3 different components. Okay, NC16, pin out, pin out, pin out, pin out. So 12 is RX and 13 is TX. So 1, 2, 3, 4. 1, 2. Yeah. So that one is TX. Let's go back to the analyzer. Start. It's not sending. Did I make a mistake? Maybe I did. And let me stop this. Okay. Oh, ZSH. I don't use ZSH on that machine. Why did I start ZSH? Okay, so UDisk mount. Okay. I don't know why it requires authorization to mount the feather. It shouldn't. So this was supposed to be writing x55. But it isn't. Seems like it's trying to do something and it's failing. Which is funny because I left this working before I left, right? Oh, no, now I remember. This is not connected. I didn't set up the clock last time on this one, so I need to actually add a clock. Well, that's going to be interesting. So as I said, last time, this thing, when I did the actual code for it, I used the crystal. But now I removed the crystal and I'm feeding the clock straight from the trinket. But I did that on the console only. I didn't actually do it on the code. So I need to actually add that. So import pwmio. I create the I²C thingy. Your clock is going to be pwmio dot wm out. This should be CircuitPython 7, so it should be working fine. Port dot that's D3. And frequency is going to be, I think I use 104,000 this time. But I'm also going to call this UART clock is equal 104,000. So I'm going to reuse that later. UT cycle is going to be 0x7FFF. And then when I create the UART, that's a baud rate, and it's not UART clock. What's the name of the thing? I think it's crystal clock. That way it will divide this correctly later. Actually, I think this was... How does it do the calculation? It multiplies the baud rate by 16. So let me do this times 16. This should work. Let's go to TO. Oh, this is trying to read. There is nothing to read, actually. Let me zero out the read, I guess. Oh, actually, that will make it... Do I have +9? No, I don't have +3 on that one. Okay, never mind that part for now. I can comment the readout because I don't care about that right now. And this is going to just print... No, remove this one as well. Yeah, it should be working. Let's go back to Analyzer and see. Yeah. There we go. And this is what I want. Because I want to illustrate in the blog, like, that's the time that you actually are sending the I²C data versus the time you're sending the actual serial data. So this is how long the CircuitPython is actually dealing with the serial port, and this is how long it takes the serial port to send it over. And that's why the discrete UART were a good option to just delegate some of the work away from the ESP32, particularly when it was not working right. Now it seems to be working fine, so I don't need this, but I needed this. At some point I needed this. And I have collected enough. So I'm going to save this capture so I don't have to do this again. So I'm going to call the create new folder. Do you actually see my... I don't. You don't see the file selector. And this is going to be CircuitPython I²C UART. And I'm going to just call it section 0. It's fine, it's fine. That's all I care. So this part does the work. That part is fine. I'm going to open a new session here. Let's go back for a moment. So Adafruit, CircuitPython, register. I think it's the name of the library. Yeah, this is the... Yeah, so this allows data descriptor... Depends on Adafruit CircuitPython. Yeah, no surprise. This is the register. So this thing just says, hey, there is an I²C bit on that thing for this device, and you can tweak it that way. I'm going to just start trying and implement this, except that there will be a few that possibly doesn't work the same way. And the reason why that is because yeah, so the problem with this one works fine. The problem with it is this works great for all of the register except for one of them, which is the divisor, because the divisor here, or divisor, whatever, it's complicated because they made it complicated, right? So this is a divisor, or whatever you want to call it. It's only can only be set. There you go, divisor latch, MSP and LSP and MSP. To access those, these are actually overlaid to the THR and IER, these two, like these two over here. But if you set LCR bit 7 to 1, then you can use these two. Otherwise, you're using the other one. Similar one of these, like 02, which is also FCR and EFR, and 04 and 05, which is MCR and LCR. Both are also enabled by setting one of these, and I forgot which one. And I don't care because I'm not using it, but some of it I can at least simplify with register stuff. So let's see what we can do about that. Find a fruit. That's IC2 bit, single bit, multi-bit register, generic structure register based on struct. So arbitrary structure register that is readable and writable, and unary struct. BCD, binary coded decimal, like this is going to, like this is great, but it also has the problem of updating. So let's start with the FCR, which is the feature control register. Sorry, the FIFO control register. And yeah, the register also supports the SPI modes. Seems coming soon, so it's not there yet. But on the other hand, I haven't actually tried the SPI stuff at all, so yeah, I²C is the only one that exists right now. From Adafruit register import I²C struct. And now I need to figure out how this is used. So simple tests over here. It does defines address. So So over here it says the register address for that register address. Oh, sorry, that's fine, yes. I do wonder how it knows. Oh, self.I²C device required by the class. Okay, that's... I need to rename it then. So let's start with that. Coding time. This thing becomes I²C device. P. No, yes. This does nothing but rename but one attribute, but at least that way I can have it self-contained. Okay. And then okay, I'm trying to figure out how it does the structure. Oh, it uses the Python struct method. So FCR has 2-bit RX trigger, 2-bit TX trigger, then reserved, and then 2-bit TX reset, and FIFA enable. I don't think I actually can use that, the struct one, I mean, because that's for like for stuff that is bigger. I can use the bits stuff instead. So what I will end up with is something like Rx trigger level is going to be, and so this is not I²C struct it once, but it's I²C bits. It's a multi-bit register, num bits, register address, lowest bit, and register width. Number of bytes in the register is 1. LSB first. Ah, that's going to be false. And signed false. Okay. So this is to see bits dot to pip. Do I have VMs on this thing? I don't. Do I not? I don't. iPhone 3 VMs. And I probably want to install this, even though it's kind of useless without the thing. At least to get the auto completion. It says to see bits dot rw bit. No, rw bits. It's 2 bits. The register address is this is going to be fun. The register address is going to be register, but because remember that all the I²C stuff is, as I said the last time, all the I²C register addresses are moved 3 bits to the left because compatibility with a different model that supports multiple channels and nobody really uses it, but never mind. The lowest bit index. So that's the thing, it doesn't document the LSB first because it says LSB first false. Okay, so let's go and look at the code. Browsing. BLTI, GitHub, there you go, GitHub. This is register. So Adafruit register, I choose C bits. Ah, there you go. This one actually has the parameters documented. Let's be first. The first byte we read from is the first byte we read from I²C. Okay, so that's LSB. The lowest bit index. Okay, so within the byte. That kind of makes sense now. Kind of, not quite, but kind of. And yes, okay, so the lowest, it's always considering MSB to the left, which is as it should be. It was just like very strange otherwise. So this thing over here, this is the FCR, this is going to be 6. Oh, this is not going to be register, so this is going to be FCR. And then the X trigger level is going to be the same, but going to be 4. And then the XV for reset is going to be I²C bit. I²C bit. I guess I need both of those because that one is a single bit. This is not 2, this is just 1. I'm just going to do. This is annoying. So I'm going to call this F I²C reg register. This is going to do the same pretty much. And this is bit number 2. Bit number 0. What the XFIFO? No, just FIFO. Okay, so that should allow the registers. Now, what this doesn't do is I'm going to have to re-merge this one for the moment. Because when I split it into multiples, it's going to be different. So I'm going to. Oh, this is going to be painful, right? Let me git stash this. So when I started writing this one, I tried to keep it as generic as possible for I²C and SPI. I'm going to make this specific to I²C for now, and like if anybody wants to add SPI support, I can add SPI support afterwards. This also is now lying because it says pre-shifted addresses, which are not. So let me actually start merging these, and then I'll figure out the rest. So this part over here can go away. And I'm going to move this part over here. And now all of this does the right thing. I'm going to remerge this one into one. Oh, except that I forgot. No, okay, git diff. I need to pass the same parameter here. So I²C and address in addition to everything else. So this gets the I²C bus and the address, which is an integer, and then everything else should work. I don't remember what board.I²C returns type-wise, but like the typing is a bit iffy anyway. Oh, sorry, don't save. I need to also rename this thing. And that means I also need to change the example to not import. Import this. Everything else stays the same. This one, it doesn't matter. So there we go. So avoid splitting the C16II implementation in two classes. Why would be nice to support this? Okay, if anybody wants to fork this and support SPI, I don't mind. Why was this doing the 3 bits? Is it reserving the last bit or not? I don't remember. Let me go and check. Like the data sheet. Once you know what you're looking for, the data sheet is actually very informative of the way the I²C naming is done. It's just that you need to know what the heck it's trying to tell you. Because it actually goes into telling you all of the details about I²C and how everything works. No, 0 is not used. So to give you an idea, this is the table that tells you how to read the addresses for the C16 IS741A on I²C. These, like bits 6 and to 3, actually match the register. 7 is actually not used either. The UARTS internal register select, but that's the actual register number it tells you. So if it says 0x01, it actually means 0x01 moved by 3 bits, because that 3 var is a 0 var. The following 2 bits will select the channel 1 or 0 for the SPI, for the UARTs that have dual UARTs, the UART on I²C, which exist. It just, this one is not one of them. So these two can only be 0 on this particular model. On other models, it will be different, and on other part numbers. And then the last one is not used. I don't know why. The last one is just never used. And if you look later, there you go. This is for the SPI. On the SPI bus, bit 7 is actually used for read or write. Oh, actually, the bit 7 uses 3 bits both ways. So that's very interesting, because so this one maps the SPI and the I²C exactly the same. So maybe the kernel is not broken. There is a Linux driver, by the way, for the SC16IS7XX. And the registers number, one of these has the shift by something on the writes. I forgot where the writes is for this one. Oh, probably the port write is the one I want. I want the definition of it. Oh, it was the first one, wasn't it? Yes, it was the first one. So I do that with reg shift here, which is true. How? Unless there is something very obvious that I'm missing on why the first bit will not be used. These only shift stuff by 2 and not by 3, which is what you need for the thing to actually work. Unless the register already pre-shifted once, because... Which, to be honest, that would not be entirely silly, right? But they're not. Like you see here, it uses FCR0x02, which is the original. I don't know how this even works. I don't know if this works. That's the other thing. I haven't tried. I'm going to just go ahead and pre-shift everything by 3. Can I add multiple cursors? Oh, I can add multiple cursors this way. Awesome. This works out very well. Okay, done. So this part helps. I mean, that's the only thing I'm changing right now. Then the next part is going to be, this is going to fail, but let's see, git dash apply. Yep, merge conflict. But it should be fine because I can just take that part over there. The read register and everything I'm going to remove later. I can delete this part over here though. Oh, made a mistake on that one. That won't work. I need to learn how to use these multiple cursors better. I'm used to block selection. Which existed on Borland. That gives you my age of what I expect. How do I read that, by the way? Settings. Okay, but I'm just going to set or equal, so that's fine. So this RX level should also be very easy. So the RX level, which is regular RX level, going back to a table of registers from a data sheet. I should probably have just loaded it on my tablet, but never mind that part. It'll be easier to read. RX level is just, both those are read-only, and the TX level and RX level, except for this part over here. Because, yeah, that stuff needs to be changed. So RX level will become, I'm going to put this first. RX level is going to be I²C bits, I guess, because, yeah, bits 8 reg RX level, starting from 0. And then this is RX LVL, because that's RX level. That should be exactly the same. TX level, like private TX level, is going to be I²C bits 8 reg TX level 0. So if FIFO is enabled, and actually that's underscore FIFO, is FCR01. So actually this underscore FIFO what I have over here should actually be if self.FIFO enabled. Besides the fact that this is probably not the fastest because I don't think this caches anything, but I don't care. I'm going to have to remove all of that as well, but one thing at a time. So if FIFO enable, return the level, otherwise return 1 if LSR 0x20. LSR tells me that THR empty. 1 if LSR 0x2. 0x2 0, sorry, so that's bit 5. Oh, actually I think I have this upside down because that's THR empty and THR is the transmit holding register. Oh, yeah, okay, I have 1 free if. Okay, yeah, that makes sense. So that THR empty is going to be I²C bit reg LSR, and that's going to be 5 if self dot this, else it's going to go away. Okay, so those are the easy ones. And that read write, like that part over there, I'm actually need to keep as it is. So the read write byte here, that's going to be fine. This is going to be that way now. It doesn't need to have a shift because it's pre-shifted. I should have fixed that before. So let me actually fix that and add it. There is no pre-shift in there. Okay. Not this, not this, split, not this, not this, not this, not this part. This part, this part, this part. Not this part, not this part, not this part, this part. Hit commit, and no, edit. Okay, so that part is done. The read write will stay there, that part stays there. Yeah, now I need to change this part over here, like the write drag bytes and write. I think the write drag 8 might need to stay, or maybe it's going to go. So that's the parity, the stop, and the bits. Those are the things that I need to change. So I'm going to call this divisor. How actually does it call it on the divisor latch enable? So divisor latch enable equal to C bit RW bit. Oh, sorry, I just realized TX level and THR empty. These are not. Oh, I need to do arrow bit, and this one is arrow bits because these are read only. And this one is a RW bit on reg LCR in position 7. And then the special registers are DLL. These are not supposed to be accessed. Oh, it's interesting. I just realized like this is write only. So I don't know if it is a WO bit. Yeah, I don't think any of these supports write only. So these ones actually are write only. I'm going to call them WO. That also means that this FIFO enabled here, it's a bit of a problem because if it is write only and I cannot read it back, I actually need to add a property for it that caches it, which is tad annoying, but we'll find. DLH. DLL, sorry. Just C bits, RW bit, reg, DLL, sorry, bits 8 are reg DLL 0 and DLH C bits RW bits 8 reg DLH 0. So those are the divisor parts there. Are the divisor actually read write? The divisors are read write at least, but you of course you need to enable it. Def divisor self value. I guess I could also put the baud rate there to be an additional wrap around that, but for now it will do. Self.divisor latch enable true. But the way I set it right in the docs. Yeah, that should work. Self.dll equal divisor and sorry, value and 0xff. Self.dlh equal value moved by 8. Self.divisor latch enable false. Property.setter of divisor def divisor again self value. Oh, this was the setter, sorry. I needed the getter there. That still means setting the divisor latch enable, and then divisor is going to be self.dll or self.dlh multiplied by 8. That should set and make the divisor, so self.divisor equaling divisor, there you go. Oh, this is going to be if value less than 0x. I'm going to actually copy paste this part over here. I'm just going to remove the baud rate part. So that means I can also do, I cannot do a baud rate unless I say the crystal thing and the crystal, oh, I can do that, but let me do that later. Try this, accept value error, re-raise value error, but with a different setting. So that removes those two parts. So now I need to do the MCR, which is the prescaler here. because of course, yeah, I really need to start wrapping that thing out later. So MCR is the clock divisor, just bit 7 of a clock divisor. So clock. We'll just call it clock divisor 4x. I²C bit dot rw bit. It's also, I think, write only, right? No, this is read write. Rag MCR 7. Instead of MCR value, blah blah blah, this is going to be clock south clock divisor 4x equal true. Not divides the divisor. So that part does the thing over here. MCR value can go away now. I don't need this anymore. FCR value, I no longer reference it because I'm using it with the other thing, but means only LCR value is what I'm doing here, which is the parity, the stop, and the bits. That part is for a baud rate. I'm going to put the parity here. So that's the parity. The parity property. No, I need the actual the parity mode. You should see bits.rw bits. And the parity is on LCR. It's 3 bits starting from bit 3 of LCR. And then stop bits is going to be I²C bit. So there's only one stop bit. Yes. C bit.rw bit. Right, LCR2. And word length, which is how many bits. C bits, rw bits, 2, right, LCR 0. And I'm going to put it this way. And I'm also going to make this into properties. This just returns the parity mode, but if I've set it, I want to make sure that it is one of those, and then it knows that it is one of them. This is important because top bits is 1 or 2, but the value setting is short or long. I don't think it's right. I think it should have been different, but like one thing at a time, I guess. Okay. That should take care of LCR here. Of course, now I need to actually do the self dot. Parity is parity. Self dot stop bits is stop, I think, right? Yes. Self dot word length is what equals bits. There you go. And self dot FIFO enable is going to be FIFO because that sets up most of these things. I'm gonna move this LCR here. Now this part over here, it's more important. Oh yeah, and then I need to do the IER now as well. I haven't done that yet. Okay, one thing at a time, I guess. Yeah, what about setting on FCR? FIFO reset. So this part over here is going to be self dot. Actually, I'm going to do that after all of that. I'm going to reset the thing. So self dot FIFO reset true. Set dot RX TX FIFO reset equal true. And then this writes to IER, which is the interrupt enable, I think. CTS interrupt enable, RTS interrupt enable, and X off. And those are all inverted. Does Datafruit have inverted? No, it does? No, it doesn't. So that's going to be interesting. Let me try to do this anyway. I don't know if this is going to work, by the way. This is the first time I try all of this. Am I calling read drag anywhere? No. I'm gonna move this right drag. I'm doing just that right drag 8. I don't care about this one anymore. So this part is the annoying one. After the divisor, after that part over there, I'm going to add this one. So if EFR is enabled, those can be disabled. What's EFR? EFR4, EFR, where is EFR? It's an EFCR, but that's the wrong one. FCR, oh EFR, sorry. If EFR4 is enabled, enable enhanced function. I'm not actually touching that, so I guess this one I don't need. Okay, so this may work. We'll find out in a moment. I do want to change that thing about the baud rate though. So set.crystal clock is going to be crystal clock. Enjoy dinner, joke. I think I'll sign off in like a few minutes if this works. Because this is essentially all I needed. I needed to get the analyzer capture saved so I can use it in one of my blog posts, and I wanted to just do this register thing here so that I could see A, if it works, B, how well it works. It looks easier to write, and probably we should be writing the MCP, the microchip IO expansor with this, because that makes it much nicer. But also still missing the SPI support. Not that I care, because I'm only using it in I²C. Like SPI will require more wires, so I don't care. Also in general, I'm not going to care much about this at all, because yeah, I'm not going to use this. I needed this because I thought I needed this because of an ESP32 bug, but may not even be there anymore. So anyway, so that set the crystal clock. Now here, actually I'm going to make the divisor also hidden, because honestly nobody should care about this one. And everybody is going to be caring about the baud rate. Which is the actual baud rate is going to be return self dot divisor. Ah, but depends. Can I actually read the clock divisor if it's that or not? Yeah, it's RW. Divisor is self.divisor. If self dot clock divisor for x divisor times equal 4, and then return that times crystal clock, I guess. Divisor is that divided by baud rate, so I'm going to multiply both sides. No, I need to get the baud rate. Ah, mental arithmetics. I'm a bit lost. Do I have a pen and paper? I don't. Let me fluff around for a moment. So, if I multiply the divisor by the crystal clock, that doesn't give me anything. Does it? I'm going to start up my tablet. Because 20 how many years since I actually did this type of things? 22, I want to say, years since I've been taught in school how to do these things in my head. And I kinda forgot. I can do them if I use pen and paper. And the problem with that is I don't have paper. I do have plenty of pens, but I only have my work stuff on it. So, but that's not something I want to use. But I have this, which allows me to write on, so that will do fine. So I have my baud rate is the crystal clock. No, sorry. Also, if that don't want a brush, yeah, I can use a pen. There you go. Ballpoint pen style. So my divisor is equal to the crystal clock divided by baud rate times 16. Now I have those ones I need to resolve by baud rate times 16, so I'm going to move it. Can you actually see? You cannot really see much of this. I need to find a way to actually cast this. Maybe if I turn this off, it's actually going to be more readable. Nope. I can reduce this so that at least it's sorta kinda. There you go. Sorta kinda. Sorta kinda will do. So the rate times 16 times divisor is equal to the crystal clock, which means that the rate is going to be the clock divided by 16 times divisor. Okay, that makes more sense now. So this is going to be crystal clock divided by 16 times divisor. So now I'm going to do the divisor. I'm going to calculate it as crystal clock by 16 times baud rate. Divisor more than 0x FFF. Dot clock divisor equal. Ha, ha, ha. So do I want to commit to change that if I'm not going to? So probably not. Oh gosh, I need to have to do this twice. Okay, we'll see. If divisor times divided by 4, if divisor still oh actually if divisor more than 0x, so ff so I need to have two things. So if it is more than 0x3 ffc, this is not representable. In this case, I'm going to raise value error, unable to configure baud rate to value, not baud rate, because otherwise things will be complicated. With the value of crystal clock, so this is value equal value, and crystal clock self dot crystal clock. And else, if the divisor is more than this thing, then the divisor needs to be divided by 4, and self.clock divisor made true, and then self.divisor equal divisor. So this allows changing the baud rate dynamically as well, and it will just do all the calculation as needed. And that means, actually I'm going to call this not, let me rename that thing. There you go, clock prescaler, better. Okay, so those should all work. Now the problem with this is, do I have a bundle here? I don't have a bundle here. I don't have a bundle at all. Okay. Did I? There you go. Can I still download this one? I can still download this one. It just to register, not like the foot CircuitPython register. It is just registered. Did I import it right? I did import it right. This one needs bus device, which I still needed anyway, and possibly Blinka, which I don't need. But I'm going to copy Adafruit register, media, CircuitPython, and I'm going to copy this as well. Go back to TO. Function takes 2 positional arguments, but 1 were given. Okay, so I screwed something up. What did I screw up? Is take I²C and an address and then a bunch of things. Which one is it? Line 129. Okay, property setter. What do you mean? Not that, not property.setter, is it? Ah, I forgot that. It's not that not that property.setter parity, is that at parity.setter. And that everywhere. You can tell I haven't done this in a while. I've been doing a lot of Erlang. I'm not fond of Erlang. Can't import name I²C. Okay, that's a bit better. I mean, still broken, but better. Can't oh yeah, it can't. No, it's right, because there is no I²C anymore. Unsupported type for float int. Ooh, 184. 184 value and okay, let me do it this way. 180. I mean, okay, now it's right. Let's see if it still works. Analyzing. BC session 1, so I don't screw up the one that I needed earlier. Yeah, it's working. It's a bit busier, maybe. Let me stop this for a second so I can compare. So yeah, the one before was sending 9 I²C bytes for sending one single byte. No, sorry, 7 for sending 1 byte and 9 for sending 3. Now it's sending 11 and 13, which means there are 4 bytes more. I think it's 1 command more, so it's not that much more. And I think what's happening is that it's reading the FIFO enable. But it works. Yeah, one of these has a false ACK here, which was C1. Yeah, I don't know what it's trying to do there, but it's like, it's okay. Like, it's working. It's working. It's actually much nicer. It's more code, but it's definitely more readable. Like, I no longer had to do the calculation by hand, and like it has all the nice setter and stuff. So let me just commit this stuff. This works. I'm going to change the readme a little bit. I'm not sure what to add to this thing, except for tested, work on. The fruit, trinket, and zero. Note this is very early release, please excuse the code drop. It doesn't add much, but it's going to be there. And I'm going to call this less in a fruit bundle requirements, the fruit register. That's the one I want. Yeah, okay. I guess I need to figure out if I can use my Blinka with the I²C with my breakout. I don't know because I don't have one. I don't have any installation of Blinka. I also think I should probably try to port Blinka on the BeagleBone because I don't think Blinka does support the BeagleBone right now, which is a bit annoying because I have a BeagleBone. Oh, I've been doing that part of the coding myself, talking to myself. But anyway, this should do the okay, now I should be able to push all of this right now. Yep, done. And I guess that calls it an evening for me. This part worked exactly as I wanted. I have the salad set up here as I needed. I have my example here, which is this whole bunch of stuff. You know, I can go ahead and record a little bit more of these. Yeah, I guess I could, if I really wanted, I could write a high-level analyzer that actually tells you what this I²C transaction does. But honestly, can't be bothered. That's honestly not something I need unless I really will need to debug this. For now, the fact that this thing just allows me to do this, and I can count like, okay, so this is the first one, this is where it ends sending a message. Then it starts sending the UART request, and then it stops here. So I can actually measure this length. Because if I use this as E0, it takes nearly 9 milliseconds to complete, probably a little less. Let's see if I try to make this a little bit more precise. Did that move T0? Yes, it did. So it took 8 milliseconds, less than 8 milliseconds to send the whole I²C transaction. And it took, so that's a 10.5 millisecond, and that's 94 millisecond and a half. So it took 84 milliseconds to actually send the full transaction, the full command. So it's a times 10. That's the most important part that this thing needs to show me in the blog, which is that the I²C compresses how much data I need to send in time. Like time compresses the data, and that's an all important part. Anyway, everybody have a nice evening. I'll go back to this another time this week. Bye.